Today, we are diving into one of the most fundamental and, let's be honest, one of the absolute weirdest properties in the entire universe, electron spin. It's this invisible force that pretty much governs everything around us, but at the same time, it completely defies common sense. So, let's get into it. So let's start with a really simple question. Go ahead, try it. Put your hand on your desk or the table in front of you. Why is it solid? Why doesn't your hand just kind of go straight through it? I mean, it feels obvious, right? But the actual reason is buried in a deep and deeply strange quantum mystery. Believe it or not, the answer is a property called spin. It's this fundamental rule that's basically baked into the source code of reality, and it's what stops the universe from just collapsing into a dense soup of energy. And how we figured this out? Well, that's an incredible story. Our story kicks off back in 1922 with an experiment that was so simple yet so profound that it just completely shattered our classical view of the world. It was the first real proof that at the tiniest scales, reality is, well, it's far stranger than anyone could have possibly imagined. So you've got these two physicists, Otto Stern and Walther Gerlach, and they cook up this pretty straightforward experiment. They heat up some silver until it turns into a gas, and then they shoot a beam of those single atoms through a funky-shaped magnetic field and onto a detector screen. Simple enough, right? Well, here's where things get really wild. According to classical physics, you'd expect those little atoms, which are basically tiny randomly spinning magnets, to just spread out and create a continuous blurry smudge on the screen. But that is not what happened. Not even close. Instead, the beams split cleanly into two distinct points. Just two. There was nothing in between. This was totally, completely unexpected. This bizarre result could only mean one thing. An electron spin is quantized. That's a fancy word, but it just means it's not a spectrum. It's not a dimmer switch. It's a light switch. It has only two possible states, a binary choice. We call them spin up and spin down. It's either one or the other, with absolutely nothing in the middle. So, okay, the experiment proved that spin exists. But that just opened up an even bigger question. What is it? I mean, if an electron is just a tiny little point particle with no physical size, what in the world is actually spinning? You know, the name spin is actually pretty misleading. Electrons aren't like little planets physically rotating in space. A much better, if less catchy name for it is intrinsic angular momentum. All that means is that it's a fundamental built-in property that a particle just has, kind of like the way it has mass, or the way it has an electric charge. The best way to think about it is like a character sheet in a video game. An electron has its stats, right? It's got a certain mass, it's got a negative charge, and it's got a spin of 1/2. It doesn't have to do anything to have these properties. They are just part of what makes it an electron. And this really gets to the heart of it. Spin isn't something an electron does. It's part of what an electron is. Seriously, if you could somehow just reach in and take away its spin, it would literally stop being an electron. Okay, and if you thought that was strange, you might want to buckle up, because this is where our everyday logic just completely breaks down. The actual geometry of spin is unlike anything we experience in our normal lives. Look, in our world, things are simple. If you turn around 360 degrees, you're right back where you started, facing the same direction. Easy. Well, for an electron, that's not how it works. An electron has to rotate a full 720 degrees. That's 2 complete turns just to get back to its original state. How is that even possible? Well, after one 360-degree turn, the electron's underlying wave function, which is the math that describes its quantum state, is inverted. It's like it's looking at a mirror image of itself. It's fundamentally changed. It takes a second full rotation for that wave function to flip back and for the electron to finally return to its true starting point. It just shows that these particles live in a mathematical reality that is fundamentally different from ours. So we've got this bizarre, quantized, internal property that needs 2 full rotations to reset itself. You might be wondering, okay, that's fascinatingly weird, but so what? What does any of this have to do with the world that we can actually see and touch? Well, as it turns out, everything. Let's go all the way back to our original question. We finally have all the pieces of the puzzle we need to understand why the world is solid. The answer lies in this absolute pillar of quantum mechanics called the Pauli exclusion principle. It's a simple rule, but it's a powerful one. It says that 2 identical particles with 1/2 spin, these are called fermions, they absolutely cannot occupy the exact same quantum state in the same space, at the same time, period. And here's the crucial point. Since all electrons are identical fermions, they have this fierce refusal to be in the same place with the same spin. It's like they have a cosmic rule about personal space. They can't all just pile into the coziest, lowest energy level around an atom. No, they're forced to stack up into different energy shells, and that's what gives atoms their entire structure. This mutual refusal, this stubbornness, it creates an incredibly powerful repulsive force. It's got a great name, degeneracy pressure. So when you press your hand on your desk, the electrons in your hand are trying to move into the space already occupied by the electrons in the desk. And all of those electrons are basically screaming, "Nope, this spot's taken." And that's it. That's the answer. The feeling of something being solid, the reason you don't just fall through the floor right now. It's not because atoms are bumping into each other like tiny little billiard balls. It is the direct, large-scale consequence of this deeply strange, purely quantum rule about spin. The solid world we live in is built on this foundation. It really makes you wonder, doesn't it? The most tangible, most obvious parts of our existence, the very solidity of the world beneath our feet, are governed by these invisible, counterintuitive rules. And that leaves us with one final thought. What other fundamental parts of our reality are built upon these strange, unseen quantum laws?